and good afternoon to all of you. I know you had a good lunch, and then now my job is to keep you awake for next some time. So we have 1 hour of lecture and then 2 hours of tutorial. So which is so total we have 3 hours that you have. Like we will be discussing today 3 hours, and then tomorrow again you will have 1 hour of me. What I will do is we can go for maybe around hour, uh, 20 minutes or so first in the first round, and then take a break, maybe for 5 to 10 minutes, 10 minutes max, and then we can come back and do another hour, 20 minutes. So if you have any, and then while we are going through it, if you have any question, put it in the chat, like two in the both two parts that we will try to cover. Like towards the end of every part, I'll try to take those questions. If there is something very urgent, of course, you can ask. You might be knowing how to raise the hand here. That function is also there, and we can take that question that way. But for the benefit of maybe the audience, it might be okay to take the question at the end. So, okay. So you had, I think you had a very good introduction in terms of what is nanoparticle, what are the different types of nanoparticle, the sizes of nanoparticle, why the size is important, and looking at the stability of nanoparticles as well. And I think in the second lecture, you had the stability in the aquatic system of the nanoparticle, how that, I think you must have discussed a little bit about zeta potential and all those kind of stuff. In this particular session, what we will do is we will be looking at, as the title suggests, that introduction to risk analysis. So what is risk? We will not go directly into nanoparticle in the beginning. We will come to nanoparticle towards the end. And then we'll talk about risk. We'll talk about in general what is environmental problems, like why we worry about doing a risk assessment. As the title of this GIAN course, as you can see, says the risk and life cycle assessment. So what is risk, and how the risk is evaluated in general, looking at in different types of contaminants, and how risk is related to toxicology. You may have heard a little bit from Dr. Pocharel on that, and you will probably hear a lot from him in the next few days. So on toxicology stuff. And so we'll kind of try to, this lecture is more kind of putting things in perspective of what are the like a real, you can say, environmental or human health aspects of, to some extent, like a negative aspects of this in this nanoparticles getting released into the environment and getting into our food chain, getting into our water. So we'll talk about all those kind of stuff. But again, before you go to nanoparticle, we'll talk about in general about in general about environmental pollutants. Okay. So let's get started then. So before we get into all these nitty-gritty detail, some of you, I do have few NPTEL Swayam courses, and so I do exist on YouTube. If you had chance to attend any of my previous course, or if you have looked into some of the YouTube videos, I tend to start with putting things in global perspective, historical perspective. So see, we talk about risk assessment, or we talk about risk management, we talk about toxicology, we talk about sustainability. Nowadays, we also talk about circular economy. But why this talk? Why? Like you should always, this is one thing which I always encourage my students to do, is ask that why question. Why we are talking about all this stuff? What is the big picture goal here? When you are seeing risk and life cycle assessment of nanoparticle, that's okay. That's one particular topic. But what is in terms of big picture? If you look at the globally big picture, where this fits in, why this kind of discussion is there? Nanoparticle is one contaminant. It could be heavy metals. It could be some organic contaminants. It could be something else. But why this discussion? The discussion is because we want to keep this earth a clean place, isn't it? Ultimately, we want this earth to be cleaner. We want this earth to have clean water, clean air, clean soil, not only for us, but also for our future generations, for our grandchildren's, their grandchildren's, and so on and so forth. So that's the big picture kind of like if you think about the whole thing, just forget about nanoparticles and all that. In general, when we talk about environmental pollution, we talk about sustainable development, we talk about this sustainability, life cycle assessment. What is the goal? Goal is to keep this planet as clean as possible. That's the ultimate goal. That's where we are. That's within that ultimate goal. These are different aspects we keep on discussing. Now, because again, we want Earth to be cleaner. We should leave it in a clean way for our future generation. Now, when we talk about that, it's when we're talking about future, let's talk about past, because that's kind of related, isn't it? So if you look at the past, and when we say the past, if you go to the very beginning, when this Mother Earth was even created, research suggests that it's around 4.6 billion years old. Let me get my pointer. So it's around 4.6 billion years old. There are some newer research which says that actually Earth is older than that. But let's forget about that. Otherwise, we'll go into those origin of Earth kind of discussion. Let's stick with 4.6 billion. So let's say 4.6 billion years old. It is if it's older, okay, that's fine. But let's 4.6 billion itself is a pretty big number. And humanity, the humans, is around 0.2 million years old, and that includes our kind of not like species even before Homo sapiens. So it's around 4.2 million years old. Now, you might be thinking that, okay, where we are going. So you will see in a minute where I'm trying to take you. So Earth is 4.6 billion years old. If you take the Earth, and as I said, let's look at the past. If you take the history of the Earth and put it in a 24-hour scale. Now, why 24-hour scale? As I said, every time I've asked the why question, why? Why 24-hour scale? Because there is 24 hours in a day. We are used to having that 24-hour timeline. We can relate to 24-hour timeline. So things is starting after midnight, going all the way around, as you can see over here, and then come back to midnight again. So that's like 24 hours. So if you take 4.6 billion years and put it in a 24-hour scale, 1 second is 52,000 years, if you put that in scale. Now, if you look at here, formation of Earth at 0, we had some meteorite bombardment for around 3 hours. Then there is the origin of life after 4 hours. We have some oldest fossils, abundant the iron formation. Then you had single cell algae after noon. So it's around 13 hours. You see that. Then we had reproduction happening, jellyfish, coal swamps. Dinosaurs doesn't come until almost what 1056, which is after noon 1056. So that's close to just like 1 hour 4 minutes before, isn't it? Yeah, it's 1 hour 4 minutes before this time. So dinosaur was around, not too far. Then we have other mammals, and then humans comes at around 1153:43. So that means 1 minute 17 seconds. And even if you go to the modern humans, the way we are today, that's actually came at almost just 200,000 years ago. So 200,000 years is like 4 seconds. Now, where we are going here with all this discussion is, say in this 4 seconds when the modern humans has been around, we have created so much of pollution on this planet. We have created variety of pollution on this planet, and we'll talk about that, how the what is the why it is happening. And we have created a huge amount of pollution and added a lot of contaminants to this Mother Earth. and nanoparticles happens to be one of that. There is a lot of other contaminants out there, as you all know. So that's just to put. And then if you look at is like here I kind of talk about a little bit of philosophical question as well. If you look at this particular map, there were species before us, isn't it? There were dinosaurs were there, and the different types of fish were there, mammals were there. So Earth was okay. Like Earth did not need humans to survive. Earth does not need us. We need Earth. And that's a huge, powerful statement, kind of hitting the ego of humans. Like we humans have a lot of ego. We think that we can control everything. We can do whatever we can, and then we will just come up with some technological solutions, and we will be we'll be controlling everything. To some extent, yes, we are like a super brainy part of different species present on this planet. But at the same time, from time to time, we get to know that we are actually on this planet maybe for few thousand years. I don't know, or maybe like two, like not few thousand years, maybe few 100,000 years. There will be a species. There was a species before us, and there could be species after us too. So humans can be gone of this planet as well. So we may not be here on this planet forever. And one of the reasons why we may not be on this planet forever is all the pollutions that we are creating. So we are actually creating our own end game. So that's where we have to have the humans survive on this planet for a longer period of time. We have to take care of this climate change issues, global warming issues, different kinds of pollution issues, which is out there. We had this pandemic, isn't it? Last 2 years. All this is March of 14th, 15th, around this time, 2 years ago. Things were started going down. And in India, I think if I remember correctly, it was March 23rd or so around that time, the lockdown, countrywide lockdown was announced. Some states even started doing lockdown before that, but countrywide lockdown happened. So, and then we were all indoors for quite some time with masks and all those kind of stuff. Even today, it is continuing, and we need to protect ourselves from this virus. Uh, so it keeps on, like we had different types of delta, then we had Omicron. In between we have lived other strain, and then we may have some more strains coming, because right even today a good fraction of global population has not even received the first dose. So I think there are more than 2 billion people in the world who hasn't received for even the first dose of the vaccine. So there is a chance that we may get some of these like some of the newer strain coming in future too. So what I'm saying is, because of these kind of events kind of tells us that the things may not be always under our control. So we need to start behaving responsibly. Now let's try to I think that was a uh, I hope it was a like a that the background kind of helps you to understand the big picture context of why we are talking about all these things. Now, in terms of the environmental pollution and all that, one of the reasons for that is having a huge population. Now, with more population, more industrial activity, more demand for resources, we will produce a lot of chemicals, and then we create those chemical pollutions, we create other sorts of pollutions. And as you can see in this map, in last 200 some years, there was a huge increase in population. Earlier the population was, as you can see, the y-axis here is global population, million axis is the time. You see almost like a zero line, but it is not actually zero, since the scale is in millions, thousand millions. So that's why you see kind of close to zero. But then from 1800 for last 220 30 years, there's a like a huge increase in population. And right now we are close to basically 8 billion people. So 7.7 billion to 8 billion people we are right now. So more people, more demand for resource, more kind of stuff, and creates uh, more environmental stresses. Are we going to see decrease in population very time soon, like overall decrease in population? Answer is no. We will see even, although the rate, the purple line is the rate. So rate of increase in population is going down. The highest rate was in 1968, which was 2.1%. And since then, it is going down. It is going down over time. Right now, we are close to 1%. This is the annual growth rate of world population. But since our base is so high, we will, of course, will see keep on increasing, and then it's supposed to go close to like 11 billion people. And right, so today we are close to 7.7 in 2019. So probably we are close to 7.8, 7.9, and that number is supposed is actually going to go up to 11 billion. So a lot of people. We will be adding like 7.7 and then 3.3. So it's almost 40%. Yeah, nearly 40% more people will be added over next 80 some years. So that will be a huge population for Earth to handle. And while we are increasing this population, what is happening is we are using lots and lots of resources. So our annual material extraction rate is going up. Our, if you look at from 1900 until 2025, from 7 billion tons to 60 billion tons is what we are, which is the annual material extraction rate for all the different activities we do on this planet. And this number is supposed to go up to 140 billion tons in 2050. So in around 50 years, the number will actually double, more than double to 140 billion tons. If you look at the increase in resource use per capita, in 1905, it was 4.6 tons of resource use per capita annually. By 2005, we are looking at close to 9 tons of, it was close to 9 tons of resource per capita. By 2035, we will have like 2 tons of resource per capita in some of the developing countries, and over 30 tons in developed countries. So this number is again is expected to go up. Now, why these things are going up? There is a lot of demand for resources because of growing population, which we looked at. Economic development, as people, as you know, across the world, as the people are getting economically well off, which they should, isn't it? They should. We should all get economically well off. That creates a lot of demand for products and creates a lot of and that's again we have to go for a more and more resource extraction. Then increasing consumption of like increasing consumption, growing middle class. So all these are leading to increase in resource extraction, increase in resource scarcity, loss of biodiversity, air pollution, water pollution, land degradation, greenhouse gas emissions, and ultimately impacts on human health. So while we were working on this demand for resources, why this nanoparticle got so popular is that when we are looking for demand for resource demand is there, we are always looking for materials which could actually, which can deliver more for less. Which you can deliver more for less. Nanoparticles, one of the important, it's a smaller size particle, of course, less than 100 nanometer, as probably you got the definition in the previous lecture. Less than 100 nanometers, that's the, and then lower the, more the activity, more reactivity. Smaller the particle, more the surface area. More surface area means again more reactivity. So because, and then it can, you can get whatever your desired function with less amount of material, and which kind of helps in terms of reducing the demand for resources. So we are always looking for newer and newer things. But thing is that whenever we come up with a newer material, since it's a man-made material, there are natural nanoparticles out there, which I think Locke may have mentioned that in his lecture earlier today. But when we make these man-made materials and introduce that to the environment, the waste, the leakages of this man-made material, and the interaction of that man-made material, that becomes a kind of interaction with your other environmental systems becomes of an issue. So that's why, and then you see that we can, how can we protect the environment, reduce poverty? One thing people are talking about, let's try to decouple the resource, go for better and better material. And then there is some examples of resource decoupling happening in Japan, Mexico City, and all that recycling. So it's not that much related to nanoparticles, but in general, we are trying to have more and more resource efficiency, if I may say that. And there is the sustainable development goals. Sustainable development goal, if you didn't get introduced to it earlier, I just wanted to just briefly kind of talk about, there are 17 goals. And whenever we are talking about this goal, there are certain environmental pollution comes in many areas, like good health and well-being, clean water sanitation, uh, like industry innovation. That will also, when you talk about responsible consumption, life below water, climate action, life on land. So all these things, all these to be like, others are also there, but to be very directly related to environmental pollutions are all these stuff. Now, when we're talking about environmental pollution and risk, I think I have given enough background to you to highlight that why these environmental, like what we are talking about in terms of environmental pollution. So I think you got a good handle on that. So when we talk about this environmental pollution, one thing is we can always look into is what exactly we are talking about when the pollution happens in the environment. Like what is the thing happening? So just wanted to give you an example to kind of set the stage what we are talking about here. So this is a leaking storage tank. Okay, this is a radioactive waste. It could be nuclear, it could be environmental, nanoparticle containing waste as well. But just but for an say if you have a leakage, if you have here, are we introducing this particular radioactive material on purpose? No, it is there in an underground storage tank, and over time it is leaking out. So when it and our one of the most common environmental pollution in terms of leaking storage tank is what? It is that our petrol pumps, which is you have the underground tank that is supposed to last for around 30 years. You will not do we like after, if we don't know whether in 30 years it has started leaking or not, because if it is leaking even in a smaller rate, it's very difficult to trace. Of course, there are mechanisms to do that. And what happens after 30 years? We're not going to take that tank out, and in most of the places they don't. So that's a leaking underground petrol gasoline tanks is one of the main cause of environmental subsurface pollution around the world, which you may, if you have taken any course on say hazardous waste management, or even talking about pollutant fate and transport, you must have discussed that there as well. So this in terms of this radioactive waste, what is happening here? We have things leaking off, and as the things leaking off, they are moving in the subsurface. Now, this particular region on the top is known as what is known as the Vadose zone. Vadose zone is unsaturated zone. Here, the pore water, whatever is the pore spaces, the porosity, the soil properties, when we talk about soil properties, the porosity, the pore spaces in the soil is filled with some moisture because of the moisture content present in the soil, but it is not 100% covered with moisture. So it has some soil air as well. So it's a Vadose zone. Things can move, air can move around this particular zone. But when it goes below this groundwater table, it becomes all saturated zone. So now we don't, in the saturated zone, we don't see that much of air. There could be some dissolved air, which is the dissolved oxygen, but you will see your air will not be there. All the white spaces got filled with water. So that's your saturated zone. So that was we will why I kind of try to define that. You will that's an important concept. Like we will be using that in terms of risk management, risk assessment. So here you have these different things coming off: plutonium, rare earth, cesium, strontium, ruthenium, nitrate, and they are moving at different kind of different. Their reaction rates are different. That's why when you see all these different lines here, they are these are called plume, Plume. You must have heard. You may have heard that. Plumes. So there is this. This is the plume of platinum. Then we have the plume of rare earth. Then the plume of cesium. Then we have plume of strontium. Then we have plume of ruthenium, and then finally nitrate. So what does it signify here? It signifies that these different, doesn't matter which are the contaminant. These are just, this is just an example. So whenever there is a release of like environmental contaminant, you see that they do not move at same rate. The movement of environmental contaminant does not happen in the same rate. Movement does happen at a different rate. Some contaminants move at a faster rate as opposed to the other contaminant. So here, which is moving fastest? Nitrate. That's why you see nitrate, because all these contaminants actually got leaked, started leaking at the bottom of this tank at the same time, but they are moving at a different rate. So now if you put this from so why they are moving in a different rate? Why they are moving at a different rate is because of the physicochemical properties of the contaminant as well as of the media at which it is. So it's not only for the contaminant, it's also for the media at which it is. These things are happening. Now, if you put a what will happen from an environmental point of view, like in terms of nanoparticles, what could potentially happen if we put this in the context of nanoparticle? Nanoparticles, a smaller particle, so will nanoparticles move faster? Potentially, yes, but it also will depend on what is there in the subsurface, what kind of reactivity it will have, whether this nanoparticle will stay at nanoparticle once it comes out. I think you talked about the stability and all that, whether it will have agglomeration, whether things will agglomerate and then it will get converted to more of a colloidal particles, or even more like bigger than colloidal particles if things kind of comes together. So it depends. It depends based on the chemistry of the nanoparticle, in which form it is, and then what kind of interactions it will have in the subsurface. But uh, so that's an important aspect. But in general, if you look at nanoparticles being a smaller size particle, they tend to be more reactive. There will be chances of them kind of creating uh, more environmental pollution kind of problem. Like if, they can even carry some of these pollutions uh, to uh, to lower to groundwater and all that. So we also kind of worry about those kind of stuff. Okay, so that's, I think that should kind of put you a little bit in context. And same thing, we can look at some other scenarios like gasoline spill. As I said earlier, if you have a gasoline spill in the subsurface, what will happen? What can potentially happen? So you have this gasoline is petrol, diesel together. It's called gasoline. Once this is your subsurface, here, this is the groundwater. So this the line below this line is saturated zone. Below the water table is saturated zone. From this point to this point is we have what is known as the Vadose zone. So that's our Vadose zone. So say there is an underground storage tank. The liquid gasoline keeps on leaking. Then it goes on the water table and sits right there. Why it sits right there? Because it's not that easily dissolved in the water. Gasoline, it's the solubility of gasoline. Gasoline is actually gasoline is not one compound. It is a mixture of variety of compounds, and the most common ones are what is known as btex. Btex is benzene, toluene, ethylene, xylene. So these are the four predominant ones, but there are other chemicals out there as well. So BTEX chemicals are, so they are not uh, readily dissolved in the water. So that's why you see a plume, you see a dissolved plume, but the reaction rate is much smaller. Had it been a very readily dissolved, so you will not see this kind of sitting on the water table. Otherwise, it will just get mixed with water. So once it's sitting in the water table, what will happen? Now you have some part of it is getting dissolved, which is getting into into the like water, soil water below. And as the groundwater is moving, it is taking it away. So as the groundwater is taking it away, so there is a again this the areas doesn't get saturated in terms of the concentration of this gasoline contamination. So you will have more and more dissolved solubility will be happening, and then you will see that taking place. Now on here, you have in terms of in the Vadose zone, what happens is since this can get volatile. This can get volatile, liquid gasoline, anything, what is volatility? Like things can get into the air phase. Now, when it gets into the air phase, uh, it can travel with the soil vapor. It can travel with soil vapor. So based on the movement of the soil vapor, based on the porosity, based on the path that which is out there, it will try to move around, and then ultimately it will try to get out on the surface and get into the atmosphere. So that is what is happening here. The vapor diffusion is happening, and then finally it will try to get to the atmosphere. If there is a building there, if there is a concrete base, and if there are cracks in those concrete, again it will try to go up. So that's and then this vapors will the wind will carry that and will take it to different locations. So and this is how your contaminants keeps on moving around. Septic tank, we are just for an example, just for a comparison, I thought I'll just put this example as well, which kind of you can which we all have seen septic tank either in our house or somebody else's house, especially if you are in semi-urban or rural area. So you have this unsaturated zone again on the top, then you have the saturated zone. We have in the septic tank, if there is this drain, like once this gets kind of filled up, if whatever is in the drain field, if things gets released from the septic tank, then you have this organic loading coming down, and then here in the below water table, you will have again this plume where things from the whatever is the contaminant coming out there will get dissolved into the water, and you will see based on the groundwater flow, the plume is moving. Plume is also moving in this direction. So, and here organic carbon is there, organic nitrogen, sulfur, chloride, and when it comes out, here the things are mostly anaerobic. But once things gets out, it becomes aerobic. So organic this gets CO2, ammonia will get converted to nitrate, and then sulfate. So sulfate, nitrate, they are all soluble. So they do get solubilized into the soil water and then go down to the water table as well. Chloride stays at chloride, but chloride is also soluble, so it can also move through the system. So similarly, like just to give, these are some of the examples. These are most common example when we talk about freight and transport. Now, whenever we try to look at these freight and transport, I'll try to go a little bit faster now. It's already but like 2:35. We have almost half an hour. We have into the lecture. So in terms of uh, uh, like a irrespective of what kind of contaminants you are looking at, when you start talking about risk assessment, risk analysis, we need numbers, isn't it? We need numbers. If I tell you that place A is more contaminated than place B, you will say, okay, that's good information, but how I can use it to make any calculation in terms of risk assessment, how I can use that information to relate that to my risk standards. So we need numbers. We need numbers. So that's why we call it a quantitative measurement. If I say that place A is more contaminated than place B, based on certain observations I have, that's a qualitative measurement. It's a qualitative. And then when we talk about actual numbers, it becomes quantitative. Now, why quantitative is important? Because it helps in defining the problem. Like it can tells you like what is the, we can measure the concentration. We can relate that concentration to the risk standard. For example, if you look at arsenic or lead, they have say certain drinking water standard. Now, one question which I always ask, and then the one drawback of this online program is I cannot see you like I cannot, but otherwise while this doing lecture, we all enjoy looking at, like we can make the eye contact and try to with the eye contact I get to know, since I've been teaching since 2008 now, so it's almost what 14 some years. So I can make out whether you are understanding, whether you are not understanding, or whether I should rephrase that, whether I should say this again in a different language, in a different way. Just from the body language, from the eye contact, we do like as you teach more and more, you kind of get that from looking at the students. But here the problem is I'm just looking at my own screen, so I don't know. But so again, if you don't, what I'm trying to say, that if you have any problem, if you're not able to, if you don't get it anything, you can raise your hand and ask questions, or you of course put it on the chat box as well. If you have any questions, put it in the chat box so that we can take it towards the end of the lecture. So quantitative, it's helps in defining the problem, which I said that, for example, if you when you look at this, drinking water standard is one of the most important parameter that we look at in terms of risk in for consumption of the water for our daily use. So and so say for example, arsenic has a drinking water standard of 10 micrograms per liter right now, and that also keeps on changing. Earlier it was 50 micrograms per liter. Today it is 10 micrograms per liter, and because we have a better understanding of arsenic toxicity, so that's why we have kind of reduced from 50 to 10. We think, and then we have a better infrastructure in terms of cleaning the water as well. So we have the infrastructure now which can treat the water to the level below 10 micrograms per liter. Otherwise, if we reduce the drinking water standard, but there is no technology out there to clean it, there's no point, isn't it? So you unnecessarily you are creating like chaos in the system. So so if I have a water and we want to see whether it's safe for drinking for arsenic or not, I have to measure the concentration. I have to know the number. If I just say that no, it has a little bit of arsenic, doesn't mean anything. So a little bit means how much? Is it more than 10 micrograms per liter? Less than 10 micrograms per liter. If it is more than 10 micrograms per liter, I'm not supposed to drink it. If it is less than 10 micrograms per liter, it is safe for me to drink it based on the acceptable risk that we have chosen. And we'll talk about that as well. So helps define the problem. You get the numbers. You can define the problem better. Reliable results from various labs. So you can get the lab results. We follow standard methods. If we know if we can quantify the problem, we can come up with a design for remediation, design for cleanup, and that's also basics of research studies used in finding answers to new problems and all that. So in terms of environmental problems, it is essentially what we look at is the interaction between the living organisms and their environment. Now, if this nanoparticle kind of stuff gets released into the environment, as our honorable director was mentioning this morning, that if you have this nano powder which you apply on your body, and if they had nanoparticles at the size of less than the pore, which is less than the pore opening size of in our skin, the chances are that some of these nanoparticles may get absorbed into our skin. And in fact, that property is being used to design some of the solutions too. Some of the solutions to certain environmental, certain human health issues, where we are trying to use nanoparticles, is we make use of that particular properties of nanoparticle, that it can penetrate through the skin. It can go into the, even if when we consume, we take, excuse me, when we go for drug delivery, that also, there also we kind of nanoparticles becomes easier to use. So but when they get into the environment, whether how it will react with living organisms, and whether it will create some adverse impact. that's where we try to look at this risk analysis and risk management part. So and there are if you look at this, basically what we are interested is living organisms and their environment interaction. So that's what the environmental problems are all. Analytical procedures are there, which uses a strange mix of chemical and biochemical methods. Then we get the data, we try to make we make a sense in terms of whether it will have some negative impacts on microorganisms or human being based on the standards. And those standards are all risk-based standards. And then many of the determinants we can also, they do fall into the like a microanalysis part. So in terms of these there are certain standard methods of analysis. Initial day, different methods proposed for the same determinant. It was leading to difficulty in comparing the data. So today there is a standard method. So when we look for this nanoparticle stuff, there is a standard way of doing things, a standard way of making nanoparticle, a standard way of looking at the stability of the nanoparticle, looking at long-term efficacy of the nanoparticle. So there is a standard method out there which try to use. So there is a comprehensive manual of the standard methods for every day we can refer to. Some of these they keep on developing, they keep on getting added up. So there is a standard methods of water analysis, which is and this also helps in terms of when things go in code. So when we get these concentrations coming out in different environmental media, we can put it in different units, parts per million, milligrams per liter, milliequivalents, fractions, and so on and so forth. And we use different things at different times. Now, if you look at in terms of our progress of pollution, unfortunately, I'm using the word progress of pollution, or let's call it different types of pollutions which is happening in the environment for last, say, 60, 70 years. Uh, we had the bacterial issues, we had the sediment issues. So we had this endpoint fecal coliform of 200 CFU per 100 ml. So we are kind of worked on it. We have treated it. We have this wastewater treatment plant where things are taken care of. Then we had these issues of BOD. We had the issues of nutrients after the like a agricultural revolution. A lot of use of fertilizers, nitrate, phosphate, getting into the environment. So we started seeing a lot of nitrates, nutrients. Before that, we had this BOD because of the fecal matter getting into the aquatic system. These are all in receiving waters. Then we had metals. We had these metals. We have persistent organic pollutants, POPs. We have ADCs, endocrine disrupting compound, pharmaceutical personal care products. And then for the last some time, we are also focusing on engineered nanomaterials. So engineered nanomaterials, ENM, is one of the focal point in terms of looking at environmental pollutants which is coming out. And if you can look at here on the y-axis, which is very, very important, y-axis is on log scale. So as we are introducing newer and newer pollutants into the environmental systems over last 50, 60, 70 some years, the level at which these contaminants are having an adverse impact is actually moving from like thousands of milligram per liter to unit, like 1 unit, like 1 milligram to 1 microgram per liter, then 1 microgram to 1 nanograms per liter. And when we're talking about engineered nanoparticles, we're even talking about less than nanograms per liter. Now, even to measure these contaminant at these levels, so there is a lot of analytical challenges. As we are moving down here, with these contaminants, it's very difficult to analyze them. We are still working on analysis methods. We are not able to cope up with newer pollutants and to come up with their analytical methods in the lab. So this is we are creating a lot of issues out there. So, but whatever is the analytical procedure out there, if you look at, there are either they do direct chemical measurement in terms of titration of the sample for alkalinity or hardness, or they go for a sensor like pH meter, chromatograph. These are example of sensors. And some places you need to do some sample preparation as well before you can use it. So sample preparation is you have the sample, you do physical preparation like mixing, drying, grinding, then chemical preparation like acid digestion, solvent extraction, chemical oxidation. Then you do titration, electrode, instrument, and all that. So again, this is we are talking about general chemicals, general pollutants, general contaminants out there. We're not talking specifically to nanoparticles right now. So there are, when we look at this instrument analysis, we can measure the pollutant level concentration of pollutant in the environmental sample. Even for nanoparticle kind of stuff, when we use this kind of method, what happens is what we get is total, which includes nano. So ionic as well as the nano forms both will be there. So these instruments, they, although if you have a just the nanoparticle, still you will see a little bit of response, because no nanoparticle suspension is 100% pure. There will always be a little bit of ionic things there, because most of this nanoparticle is made, especially the engineered nanoparticle is made from ionic form. So reaction is never 100% complete. So you will have some residual ionic form always present. So these instruments, they give a response that correlates the amount of sample present. For example, the response could be increase in conductivity, absorbance of light, emissions of light, and so on and so forth. You had some discussion around nanoparticle this morning. So just a question, and if any one of you want to answer, you can unmute yourself and answer. If that's say if you have a pure nano suspension, if you have a pure nano suspension, what will be its conductivity? Anyone? What would be a conductivity of a pure nano suspension if it's 100% pure nano suspension? What causes conductivity? It is the dissolved ions. So that was a hint. So what would be conductivity of a pure nano suspension? Anyone want to give a try?
Ideally, it has to be 0.
Yeah, that's correct. It has to be 0. And that's one aspect actually we use to measure the purity of nanoparticle, especially those nanoparticle in which the ionic forms can get into solution. Like if I'm looking at nano silver, and nano silver, which I think if you, Dr. Lok Pokharel will talk about that in great detail, because his PhD was on nano silver, zinc oxide, and titanium dioxide. And then he may tell you about the same thing, that how when we were like, as I mentioned this morning, he's my first PhD student. So when we were working on this nano stuff, we were actually worried about whether, see, we are looking at nanotoxicity. Now, if I'm using silver nitrate and making nano silver and taking that sample and trying to do the toxicity test, how can I be sure that the sample, that the solution that I'm using, that sample that I'm using is only nanoparticle, does not have ionic form of silver? Because when I'm doing the toxicity test, my ionic form may be response of ionic form may be different than the nano form. If I'm looking at nanotoxicity, so it should be directly from the nano form, not the ionic form, isn't it? So if I'm saying nanotoxicity, but actually what is happening is my sample has significant presence of ionic as well. So that will actually give me a negative, that will give me a wrong information. That will give me basically ionic toxicity, or a mixture of ionic and nanotoxicity. So to see the purity of nano suspension, we measure its conductivity. And we can see if it's closer to 0, that means it is mostly nano. Its ionic form is not there. And in the project that Dr. Lok Pokharel worked on, we had this was actually what the project was funded, is to look at the toxicity specific to the nano form. And I'm proud to say that our lab was one of the first lab in US at that time, when I was working in US in Tennessee State University. That our lab was one of the first lab to show the toxicity information specifically from nano. And we had a separation system as well, where we could take the ionic form separate, the nano form separate. I will not go in detail, because that's Dr. Lok Pokharel's PhD, and I'm pretty sure he will talk about that at some point of time. He has a long list of lectures with you guys, so I'll not take his material out, and that's why Dr. Bandidharan has asked me to focus on in general risk assessment and then how it relates to nano. So I'll keep my thing in more in general, and then we'll talk about nano as well. But I don't want things to be repeated too much. So, but you will hear a lot from Dr. Locke Pochrel on that aspect. So whenever we go for this instrument analysis, uh, this is we come up with this particular curve at the beginning. This is called your dose response curve, or you can say the dose response curve, or what is actually it is a calibration curve. Our dose response curve is slightly different. We'll talk about that in a minute, in a few minutes down the line. But this is the calibration curve. Before we analyze any sample, we put the known concentrations. So these are our known concentrations that we have given to the sample, and then we got the response. And from these known concentrations, we got this best fit line. Sometimes it could be linear, some it may not be linear at sometimes. Now what will happen is if I have a sample, I put the sample through the system, I get a response, and then I bring that response to this particular line, then drop that down here, and I get what is the concentration of that particular contaminant. So, and the response could be increase in conductivity, absorbance of light, emissions of light, and other things as well. Okay, so instrumentation analysis, spectrophotometer is very common. Some chemicals are directly proportional to absorbance. But if you have some things where you have, if you have a sample is colored to start with, it's very difficult. But if you have a clear sample like here, which on reaction with certain reagents changes color, and then the absorbance will change, absorbance reading will change from here to here. Darker the color, usually more the concentration, or we can analyze using that spectrophotometer. Whenever we go for these analysis, you have to do quality assurance, quality control in terms of making sure the data is correct, data is reliable. We look at some blanks in terms of some contamination happening in the lab, some spikes, some replicates, to make sure the instrument is working properly. So we do all those kind of stuff. Whenever we do some measurements, the instrument will give you a number. Now, how do you trust if the number is closer to zero, if the number is closer to the detection limit of the machine? See, every machine has a detection limit. Every instrument has a detection limit. You cannot have you cannot measure zero. Earlier, I said that arsenic drinking water standard is 10 micrograms per liter. Now, ideally, if you say, we all know that arsenic is carcinogen, in the state of West Bengal, in several other places in India, and the country of Bangladesh, we are seeing a huge, and other countries like Vietnam and other places too, we are seeing arsenic pollution and leading to cancer and all that. So why not put arsenic as zero concentration in the water? Why even go with 10 micrograms per liter? Let's make it 0 micrograms per liter. But the reason why it is not zero, because you cannot really measure zero. You can have something below detection, but below detection does not mean it is not there. So for any instrument, what is that below detection limit? What is that detection limit at which you can say for surety? Here we are getting into statistics, that minimum concentration of a substance that can be measured and reported with 99% confidence. That your concentration is present, it is greater than zero, and so that is what is known as the method detection limit. So how do we calculate that? We take this is the formula for method detection limit. It's your t value from the t test. N is your number of samples, so n minus 1 is your one-sided like a degree of freedom, one-sided critical t value at 99% level. We take that. S is the standard deviation. So so in terms of MDL, it can be calculated by multiplying the standard deviation by one-sided critical t value at 99%. So different t value should be applied. EPA recommends that have minimum of 7 samples. So minimum you keep 7 samples when you're trying to go for method detection limit calculation. So what you do here is essentially you take the same sample, analyze it for seven or 8 different times. Minimum was 7, so here we'd say that 8 times. and you get the values. This is the same sample, but since there will be variability in the machine, you will not always get the same value. You will get, although you will get similar values. So it started from 12.02 to 12.57. So that's the range in which we saw that 12.02 to 12.57. So if you, this is the same sample ran 8 times, and then we have to get what? If you remember here, we have to get the standard deviation. And so, and t values. So here n is 8, so n minus 1 will be 7. So we will find out for degree of freedom 7, 99.99 confidence interval. We can find out the t value from the t table from your statistics. And I'm assuming that all of you have done some form of statistics class. And then so n is 8, standard, and the standard deviation S could be calculated as 0.19 from those 8 data sets. T value is 3. So it becomes 0.19 multiplied by 3.57 milligrams per liter. So what does it mean is, it indicates that this is the minimum concentration you can trust with 99% confidence level for this particular pollutant, for this particular element that you are trying to analyze. So similarly, we can do it for other animals, other elements too. So in your lab, all of you who are working in the lab, if you're doing your PhD, you're doing different kind of masters or PhD or even some research, you're looking at different contaminants. Try to, when analyze using certain analytical instrument, always you should have an idea of what is the detection limit of that particular instrument, so that you can report your data with a confidence that if it's more than that, you are sure. But you see, if you put something in the machine will always give you a number. Sometimes even you get, those of us who has worked in the lab, we have seen even the concentration coming out in negative sometimes, which is of course not true, which is, it's wrong. But since it's machine, it will give you a number. So in case you get it for this particular element, for this particular contaminant, if you get a number below 0.57, it says that you cannot trust that number. The number is not trustworthy. We cannot report that number. So anything below detection limit, we just say it is below detection limit, or we just say below 0.57 milligrams per liter. We cannot say, we may get a number like 0.3 or 0.2 or 0.1. We cannot report those values because those values does not make sense. Machine cannot detect a concentration below 0.57 milligrams per liter for this particular contaminant that we are talking about, and for this particular in this particular analyte that we are looking at. So that is also very, very important. There are different types of instruments out there. These are some old pictures that I had taken. So I just put, just to very quickly tell you what are the instruments typically used for different environmental contaminants. We have ion exchange chromatograph for different ions, then gas chromatograph to measure the gas samples, even the liquid samples, which is getting converted to gas. So GC helps in a lot of organics analysis, complex gas and liquid samples. Gas chromatograph MS. Here again, complex chemicals. We can separate through GC columns, and then built-in library kind of tries to correspond. So it tries to do some detective work here. I try to find out what components can potentially be present, and then we try to check that whether it's present or not using further GC analysis as well. HPLC is uses to more complex, greater molecular weight chemicals. We use it for even doing for pharmaceuticals and those kind of things too. LCMS is used a lot for pharmaceutical products and protein and all that, which is similar to GCMS, but here liquid chromatograph. ICP is mostly used for heavy metals. Same thing as AAS for heavy metals. You can use that for heavy metals and metalloids. So we get a lot of, we take samples from the environment. We go for whenever, see, one of the one of the first step of risk assessment is to find out what is the level of concentration, what is the level of contamination, what will be the exposure scenario. So that's what so far I was trying to explain to you, that in terms of the risk analysis, the first step is anywhere you go where the contaminated site is and you're trying to assess the risk, you will go there and try to take sample. You will bring that sample into the lab, and you will do all these analysis. You will go through all these analytical instruments. You will make sure that the method detection limit is known. You will make sure that we do proper replicate, proper QA/QC is there, because that's a very, very important aspect of risk analysis and risk management. Unless we are sure of the contaminant level, next step cannot happen, isn't it? So to make it surety of contaminant level, those things is very, very important. So that was the number one step in terms of the risk analysis. Try to get proper uh, concentration level, proper exposure level for water, air, and all that. So here, um, so we have, so once you have this concentration, you can work with those concentration. You can do a lot of stuff with that. Just here are some examples. For example, if you have a sludge with total arsenic concentration of this much based on total weight, moisture content is this, what is the dry arsenic weight? Now, why dry weight? Because all the soil standards, and they are all based on dry weight, because the moisture content can vary from one soil type to another soil type. So they work on dry basis. So here you get from zero 0.6 milligram arsenic per kg of wet sludge, you get like 3 milligram arsenic per kg of dry sludge. So that's 3 mg per kg of dry sludge you are going to get. So that's as you can see, from 0.6 it became 3, and this is what you will compare it with. If you want to use the sludge for any application in soil and all, that becomes your basis for comparison. We can also take average. That is also, we can, if there are different types of waste, they're mixing together, we can take an average. For example, sludge is there with some lead, and wood chips has also had some lead. This is 100 milligram per kilogram in terms of wet waste. Solid content in the sludge is 10%, so moisture content is 90%. Wood chips 300, then moisture content is 20%. And if you have to mix it together, say if you're mixing it in 50-50, what will be the resultant lead concentration in the mix? So if you mix it by 50-50, and what will be in the dry sludge, these are all based on the wet. So we have to convert that into the dry. So what we'll do with the number one is, we'll try to find out the total amount of lead present. So we'll do a mass balance, total amount of lead. The mass of lead is not going to, whether it's a wet or dry, mass of lead will stay as it is. Mass lead will not get volatilized or vaporized. So you will, so what we are doing on the top here is actually getting the total amount of lead present. So lead coming from the sludge, lead coming from the wood. So 1 kg of wet sludge, this was the given 100 milligram per kilogram, and then 50 kg of this, 300 milligram per kilogram, 50 kg of this. So we got in the numerator, we are getting what is the total amount of lead present. And since the number one's in terms of the dry weight, so in the bottom, we converted that of the wet to dry based on the moisture content in both the cases. And we got what is the dry weight at the denominator. So, and then finally, the number you get around 444 milligram of lead per kg of dry waste. So those kind of calculations can be done. You can also look at between total and leachable. For example, if you have a soil contaminated with lead-based paint debris, if you want to find out whether this will be a hazardous waste or not, we do hazardous waste testing using what is known as TCLP, and that is used for hazardous waste analysis. But if we say if you TCLP says that you take 100 grams in 2 liters, so 100 grams and 2 liters of solution, if you can take that, if say this is the concentration of lead in the soil, and when we are using 100 grams in 2 liters of solution, assuming that all the lead present in the soil gets dissolved into the water phase, which does not happen in realistic, but we are taking the worst case scenario. So in that case, if you can find out the X, it's around 100 milligram per lead per kg. So if the concentration is below 100 milligram per lead per kg, we don't have to go for this leaching test. We don't need to go. We can just say for it will not be a hazardous waste. So if we know the total concentration, we can say that the chances of it being a hazardous waste is not there because the concentration is less than 100. If it's more than 100, of course, we should go for all those testing. Similarly, you can, when things are applied into the outside atmosphere, you will have the rainfall interaction with them. So when you have rainfall interaction with them, things will leach off and will go to the subsurface. We can go potentially to the groundwater. Here, SPLP is a synthetic precipitation. So synthetic rainfall, we simulate that condition doing some lab-based test. and then try to get the numbers and compare that to the groundwater standard, because that's what potentially it may happen. Things may go into the groundwater. So, and so very quickly, I'll also show you that how the statistics becomes important. Say if you are looking at this hazardous waste thing only, if you are looking at it's like a set of samples where you went and collected some samples and try to look at whether things are hazardous waste or not. Uh, so what you get, try to get and get the number of samples. More the number of samples, better it is to get a representative samples. More the heterogeneity, more the samples is required. And then you look at its mean, median, mode, and all that, average, middle number. So there's those kind of stuff. And what kind of sample distribution, because most of these statistical things assume things to be normal distributed. So either it's normal or log normal distribution. So you also look at those aspects. And I'm going a little bit faster because I'm assuming that you must be familiar if you have taken a basic statistics course, which you should have taken it. So you must be familiar with all these things. But if not, you just ask me a question. Okay, so this is a data set with a number of samples, 29. These are the data set in terms of the leaching result of TCLP. If the number goes above 5, it's a hazardous waste. So, and then you draw it, you get arithmetic mean, you get median, you get mode. It shows that this histogram does show that it's a normal distribution. It's a typical bell-shaped curve. So we can, it's a normal distribution. And then there is another data set, which is you see the TCLP results like here, where the variability is much higher. Value goes from 1 to 16. In the previous one, you may have seen that variability was not that high. So if you plot this one, it becomes more of a kind of a long tail, indicating that it could be a log normal distribution. It may not be a normal distribution. You get this arithmetic mean, median, and mode. And we do a test, quick test, check for normalcy. If the mean is greater than standard deviation and variance, the chances are that it's a normally distributed. If mean is not greater than both, then data set is probably not normally distributed. So taking this check, if you can take those two data sets, the first data set is normal distributed because the mean is greater than standard deviation and variance. In the second one, it's not. Mean is greater than standard deviation, but lower than variance. So it's non-normal distributed. So what it could be, as the graph suggested, as the histogram suggested, it could be log normal. So we do we transform the data set. We transform into a log normal. Most likely environmental samples are mostly log normal field samples. So we do the log transform data and then do this calculation again. And we find here the arithmetic mean is actually higher than standard deviation and variance. So the transform data is normal distributed. That means the original data is the log normal distributed. So, and then we calculate the mean. We got it on 4.28 milligram per liter. So that's called geometric mean. So sometimes in the papers and reports, you will see geometric mean, not arithmetic mean. Arithmetic mean was data set was normal distribution. If it shows geometric mean, that means the data set was actually log normal distribution. So if it's not normal or log normal, what you will do? You can try to find another distribution, use more advanced statistical methods. So those are beyond the scope for today. But you can look it up. You can learn about more, and if you you can do that. So this is again, what we did was we collected a lot of samples, and we did the analysis in the lab, and we got these numbers. But what does that number actually mean? How it relates to the population mean, the main population mean? So arithmetic mean for the data set was 4.83, the first one, and the geometric mean for the second data set was 4.28. Now, they are both less than 5. So if they are less than 5, means it's not a hazardous waste, but it's pretty close to 5, but it's not more than 5. But these are based on limited number of samples. Now, if you have to take it to the true mean, remember that in uncertainty principles that we have learned in statistics. So we put that upper confidence level, lower confidence level. So we try to put that like a concept here. And if you go for 95% UCL, that is defined as this, like mean plus t values for alpha n minus 1 is standard deviation is square root of number of sample. So if you take these two samples, take these two sample sets and do that for the data set 1, we got it's like 5.46 milligrams per liter. Note that this is higher than the toxic limit of 5. Although arithmetic mean was 4.83, but when we did that, what is the chance that 95% of the 95% of the samples will be, what will be the, what is the upper confidence limit, what could be the potential concentration, we get the value to be more than 5. Same thing in the second test too, it's more than 5. And here, as you can see, we did it on the log transform data, we got this number, then we took the e to the power of that to get this value. So that's your log transform data. So in both the cases, it is failing TCL. Now, what to do? So we will have, again, these two data sets were, it's not a real data set. I have created the data set just to give you, just to illustrate the point that this is important, like these kind of scenarios can happen in when you are looking at real world problem too. And then you have to come up with how to handle those situations. So, and if you get the data below detection limit, so can you use that data? You cannot just write BDL below detection limit, because when you do the Excel calculation, Excel likes to have a number. So what number you should put if the data is below detection? So some people say that you can put 0. Some people say we should have put it as a detection limit. Some people say half the detection limit. Most popular one is actually the half the detection limit, because their logic is some values could be lower than that, some values could be upper than that, so it kind of nullifies it. Okay, so we kind of learned so far in terms of like how what are the different, we started with looking at big picture in terms of environmental issues. We also looked into how the population, economic activities, and all those resource consumption, they kind of impacts environment. Why this materials such as nanoparticles, engineered nanomaterials are becoming more predominant, more popular, because it can do more for less resource consumption as well. And it has some variety of properties which we can use. And then we also talked about that when you have this environmental contamination in terms of what kind of sample collection, how to do the sample analysis, what are the standard methods of doing certain things, what is in terms of how will you go about doing analysis for different types of contaminants. And then once you have the number, once you have the quantitative number, before that we also looked at qualitative versus quantitative. And then in terms of quantitative numbers, if you have the numbers, what does the number mean? And how to make sense of that number, and how to take the lab-based data and try to come up with what can potentially happen in the field. So we looked at some of the examples as well. So those are kind of gives you kind of, and we talked about how it is related to risk analysis, the first aspect of the risk analysis. What we have talked about so far is actually the first aspect of risk analysis, which is trying to come up with hazard identification and finding out the concentration levels. So exposure levels. So that's what we have focused on so far. Then now we'll look at, okay, once the concentration is there, what kind of exposure it can have, and where it can be, whether if there is a chemical is released into the environment, what happens to that chemical. So let's, I think it's what it, we are almost like we are exactly at the middle of this 3-hour slot that we have of 1 hour plus 2 hours. So we can, let's take a maybe break for maybe 5 minutes. You can stand up, stretch your hand and leg a little bit, and then you can come back in 5 minutes. So it's, and then we can start. Okay, grab some water, grab a coffee, and whatever you want to do, and we will start in 5 minutes again. So I'll stop sharing for a minute, and I'll look at if you have any questions on the chat. There is no questions on the chat. Any question you want to discuss right until this point? Any question, any comment? Does it all make sense? Do you see value of why this kind of information is important? See, this is the problem of online teaching, which we are which we are experiencing in last 2 years, and that it looks like you are talking to the blank screen. So anyway, let's take a break and then think about the questions. We will in 5 minutes we will again come back, and we will if you have any question, we'll take that, and then we'll proceed further to the next part of this lectures, and that's with some case studies as well.
Okay, sir. We will meet in 5 minutes, sir. Oh,
yeah.
Yeah. Okay.
Okay, so let's any question? If not, then we will keep on making further progress.
Yes, sir. We can move on, sir.
Okay, so let's I'll share my screen again. Okay, so we were talking about these release of chemicals into the environment. Oops, sorry, I think it was already there. Yeah. So whenever any chemical, whether it's a nanoparticle, whether it's an ionic particle, whether it's a colloidal particle, whether it's like whatever it is, when it gets into the environment, it can come to the atmosphere, it can go to the surface water, it can go to the land. So how it gets there? It could be, as our honorable director was mentioning this morning, that like burning, either legal burning, like people using a lot of firewood and all. Those are and that also creates a lot of aerosol and those kind of particles, which again has particles, particulate matters, PM particulate matters, different sizes, PM10, PM2.5, even less than that. You can have airborne particles in nanoparticle size as well. So those are things are there in terms of getting into the atmosphere, illegal burning. From land treatment facility as well, when you are a sewage treatment plant, when you flare the gas, that also creates different types of particles goes there. From aeration basins and all that, that will be that volatile compounds which gets stripped, that also goes to the atmosphere. Then we have seen that a lot of chemicals does get released into the surface water. And this toxic release inventory is a inventory done in as part of the US EPA's monetary program in the United States. They have seen that around close to 220 million pounds of toxic chemicals get released in rivers, lakes, ponds, streams per year. So that's a lot of toxic chemicals goes into the air around the world. And mostly coming from chemical manufacturing, primary metals, paper, food processing, those kind of industries. So there are regulations out there. We have the regulations out there to control that. The regulations are all based on the risk assessment only. So things does from the landfills, things get into the land. There have been cases where we are worried about looking at if this nano waste, nanoparticle containing waste getting into the landfill. Now we have the liner system at the bottom. Now this liner, whether it will be with if the nanoparticle stays as nanoparticle, whether if the particle size being so small, whether it will penetrate through the liner. If it can penetrate through our human skin, it can penetrate through the liner too, and it can go into the subsurface. So those kind of issues are there. So that's those kind of things we need to kind of look at. Uh, so in terms of other kind of contaminants, we do see from the hazardous waste things coming in there. Uh, but whenever things goes into the environment, there is a natural treatment process, like natural attenuation. We call it attenuation, how it happens, which over time reduces mobility and toxicity of the contaminant. Mobility means how the contaminant will move, and toxicity is of course a harmful level of that. So we do see significant quantity of these releasing to the water, surface water, land, subsurface. So we have to understand the risk, understand the real risk of these. We have to understand the fate of these stuff, how things will move, what is the movement, fate, and disposition. So how whether the how the concentration will be in terms during the exposure, whether the concentration is going to increase or decrease, the time over which the exposure will happen, whether it will be in the air phase, whether it will be in the liquid phase, how quickly it disperses, how quickly it accumulates, how quickly it decays, what is the residence time. These are all important stuff to understand. And there are whether it again whether it's in the surface water, whether it will go into the groundwater. Uh, so certain things are soluble organics can transfer to the groundwater. There are many things which may precipitate out as well, maybe just part of the soil, like, or may go into the sediments and just be there, get deposited into the sediments, does not come back to the system, to the water again, or it may come back to the water depending on the cycle, based on how things are happening there. So if you look at some of these risk, like a big picture example of different classes of chemicals, which has created problem, like heavy metals, which is one big group. Now, many of these nanomaterials, when we talk about nanomaterials, they are, if you talk about nano silver or nano, say, if you're looking at even like in zinc oxide, which is again zinc is there, or titanium dioxide, or quantum dot, which is the cadmium and selenium. So these are all heavy metals or metalloids. So they will, once it is out into the system, they are expected to have actually more severe toxicity as compared to the metallic ones, because since they are in nanoform, they can penetrate through the system much easier. So, but if you look at in terms of metallic toxicity, toxicity of the heavy metals, some of the predominant examples, if you can just quickly have a look, the Minamata Bay, which is the methyl mercury, which is very, very famous, where we had this mercury pollution into the water, in the standing water. That water was in the paddy field. The water came from an industrial facility. When this mercury, the mercury got methylated in that atmosphere, so it became a methyl mercury. Methyl mercury is more mobile. It can even get volatile and can travel, and that created a lot of exposure to the people. So, and the groundwater is, we have to, when you're talking about this exposure, groundwater is one major source of drinking water. Most of the 50% of the world population is dependent on groundwater. So we don't want any of this contaminant, whether it's nano, non-nano, it doesn't matter. We don't want any of this contaminant to reach the groundwater. So when we talk about this risk assessment, we have to look at in terms of depending on the depth of the water table, how far these things can travel. So see how it will reach. It will be in surface water. So all the groundwater originates at surface water, then it kind of gets recharged. So things can go liquid waste and disposal pits, impoundment, landfill, other land applications. It can create solid and semi-solid hazardous waste, which will kind of leach out some of these chemicals into the subsurface. So they do underground one or more several mechanisms. It can travel through. If it's a volatile stuff, it can through the soil pore, soil vapor. It can travel through soil vapor as well and go to the water table, and those things do happen. Contaminant may sorbs into colloid and then get transported to the, when it becomes mobile. That's another concern with nanoparticles. Contaminant can get into the nanoparticle, has a like a surface activity is much higher, the higher surface area, so good adsorbent sites. So these contaminants can get adsorbed to this nanoparticle, and the nanoparticle can carry it through the different media because of its a smaller size, and then can take it to the groundwater much quickly. So those things are also being looked into. We talked about mercury already. So when we talk about, when we say risk, the thing of toxicity is very, very important. So when we talk about toxicity, whether we talk about toxicity to humans like cancer, non-cancer impact, toxicity to the ecosystem. In terms of the human, we say there are two broad categories: whether it is going to cause cancer or whether it will have an impact of a non-cancer. Both are important, but cancer is considered more deadly. So in the ecosystem, you have the individual organism, population level organisms, community level impact, and all that. So many chemicals have been found to be human carcinogens, like arsenic, benzene, hexavalent chromium, vinyl chloride. Those all are considered to be human carcinogen. They create different types of cancer. Chemical causes cancer in different manners. The time of exposure and initiation of cancer can be large. So that's called gestation period. It's very difficult to identify the cause of the cancer, because since we get exposed to so many different chemicals, it's very difficult to identify what could have caused the cancer. But they are discovered from how we find more information about is that when we look at some certain incidents of population exposed to abnormally large concentration of concentration of that particular contaminant. That's what we saw for arsenic in Bangladesh or parts of West Bengal, where we already know that people got exposed to it. Then we try to correlate. That's called epidemiological data. Epidemiological data is what we looked at there. And or we can look at the studies from the lab animals. So for non-cancer effect, it can target certain organs like liver, nervous system, kidney, reproductive system, development. So how do you quantify toxicity? Say it's we were saying that we will do risk analysis. So number one part, we said that okay, we found out the hazard, we found out what chemicals are present, and then we got the concentration. Now we got the concentration, so we know the exposure level. Now, once we know the exposure level, we can calculate the toxic effect if we know the potency, because the toxic effect is potency times exposure. So this potency we calculate in the lab based on the toxicity test. So if you know the top potency based on the lab-based results of that particular contaminant, and if you know the exposure level of the contaminant, we can come up with what is the toxic effect. So it is not just how toxic a chemical is, it's also that how much of an organism is exposed to that chemical. Say if a chemical is quite toxic, but you just got exposed to, say, microseconds or milliseconds or a few couple of seconds, as opposed to something which is relatively much less toxic, but you're getting exposed to 8 hours a day, every day during your work, you're getting exposed to it. So your toxic effects in the second case will be higher than the first case, because your exposure duration was much higher. So that's what you need to look at. So how do we quantify? We try to get lab studies or epidemiological study, as I mentioned earlier, and we look at the different toxic level. So we come up with what is known as this. This is the curve, typical curve of dose response. We come up with this dose response curve, where we take. This is the exposure. This is the impact. We start from the beginning, initially to certain up to a certain limit. There is no impact, so it's basically zero. You see a zero thing. But then you start seeing gradually kind of seeing more and more impact, and then you see a kind of plateau. It gets flattened here. That's your complete impact. So it's a dose response curve. It is also called like letter S, as for Sam, curve, because it kind of makes a S shape, kind of a little bit of a stretched S shape, as you can see over here. So up to this point, there is no effect. So that is null, no observed adverse effect level. Then we start seeing some observed. So this is the lowest observed adverse effect level. So based on the data that we have collected. And then this is one aspect which is quite important is we calculate EC50, the exposure at which effect is occurring in 50% of the population. So that is important to know. So this is what we can get out of the lab-based results. But when you are looking at the human data, human epidemiological data, you can have some data points. You probably will have no data point here, because there was once there was no exposure, we did not measure any response. We measured response here by accident, because these things did happen. Then we found out, okay, what was the impact level, and what was the this contaminant level in their blood sample, urine sample, and all that, or hair sample, and we kind of correlate. So you have just this few data. Now and this is a very important data, but since the data is so limited, what can we do with this data? So we use certain models. We try to model this phenomena, and try to come up with what would be the potential in terms of concentration at the lower exposure level. So we come up with that. So here we can estimate exposure. What exposure is acceptable for non-cancer? We try to find out the exposure which doesn't have any effect, no response. But in cancer, we say let's go for a acceptable risk of 1 in a million. So if 10 micrograms per liter for arsenic, if somebody is, if I'm consuming 10 micrograms per liter of water, like arsenic containing water every day for my water requirement, there is a possibility that I may get cancer, like where I can have one excess cancer in 1 million. So 1 in a million cancer risk, I can have that scenario. That is because it is based on 1 in a million. So why because many of these carcinogens are pretty difficult to, very darn difficult to treat. It's a lot of treatment costs. So we have to kind of live with some risk. So the risk here is typically 1 in a million. So we kind of look at 1 in a million risk and stay with that for most of the carcinogen. So for non-cancer risk, we calculate reference dose milligram per kilogram per day. So we take the lower or novel value and then apply a lot of uncertainty factors, because those data collected in the lab is on mice, rats, or guinea pigs. and we are trying to expose it to humans, so that we are trying to apply a lot of uncertainty factors there, account for unknowns that are different in the species, exposure duration, and all that. So based on then we calculate how much of milligram per kilogram per day in terms of the body weight you get safe. So for example, here cadmium, it's this much for water, this much for food. For it is much less for water, more for food. Again, as you can see that water, if it's in water, it's easy to get into the bloodstream. So that's why the number is smaller for water. If it's in food, it will get consumed and then it will get digested. It will come into our system. So part of it may not come into our system. So that's why it is. It has like a different number right there for oral RFD for food. There is no inhalation because cadmium doesn't go volatile. So you can, this particular website, you can find reference dose number for all the contaminants that has been tested so far. Slope factor is for the cancer risk, where we try to look at the fraction of population affected per milligram per kilogram per day. And here also 1 in a million. So in terms of how will you extrapolate the slope factor? Much of the human carcinogen data is based on high exposure, high risk, as you saw. So we get these kind of data, like high exposure, high risk data. Now, how we can take this and extrapolate it to the lower concentration, because if we want about 1 in a million, so if you can draw the line here, so the concentration should be, exposure level should be this. Or if it goes up to up to this point, then the exposure level is somewhere over there. Now, here, like whether we can go this way, or we go linear, or we go this way, very difficult question. For the chemical which is more potent and lower concentration than predicted, we try to kind of go to that particular model. Based on some of the lab-based study, we kind of have some idea what can potentially happen at the lower concentration to the different species, not to humans, but to other species. And then same thing, chemical, if is less potent and lower concentration, as opposed to what we saw here, we kind of go for this particular curve. And we can model these things. There are statistical modeling of risk analysis. So they basically do this kind of exercise. So this is so in terms of getting this toxicity information, along with its exposure duration and frequency, we can come up with a risk posed by the contaminant present in this contaminated soil or waste or water or whatever. And then based on that, we can use protective limits. Now, protective limits is what is, say, as I said earlier, is in terms of the standards. So drinking water standards or soil standards and all that. So in terms of drinking water standard, this is how typically for carcinogen, the drinking water standard is calculated. So you have drinking water in milligrams per liter. This is the target cancer risk, which is what, 1 in a million. So that's your TR value. Body weight, typical body weight, say 70 kg for a human. Then oral cancer slope factor, which we calculate in that particular, taking that particular data, epidemiological data, as well as some lab-based data, we get this value. And how much water we consume, like 2 liters per day, if you say that. So taking all these values, we can calculate what would be the what should be the drinking water standard. So that's how this 10 microgram per liter number was calculated. For non-carcinogens, we have the oral reference dose, as you saw for the cadmium. Similarly, you will find it for all the different contaminants, potential contaminants. Then body weight divided by the water consumption. So that's what you get it for, what should be the concentration for non-carcinogens. For soil standard or even compost standards and all that, again, target cancer risk, 1 in a million, body weight, oral slope cancer factor, and ingestion rate. Now, this ingestion route is, say, if you have a contaminated soil, you touch that soil and you put that hand in your mouth. So that's your ingestion rate. So we calculate that. There is a method, there is an way of experiments can be designed to do that. And we estimate that particular ingestion rate, and then we use that value in this particular equation. So that's kind of some basics on toxicity. Now, when we talk about this toxicology, which you will learn, I think Dr. Lokpokharel will cover these things slightly in more detail. We are looking at different chemical society. It's a chemical world. So we are chemophilic and chemophobic society. Chemophilic is some of part of our society is they love chemicals. We make variety and variety of chemicals for different applications, different uses, and it does help the humankind. But when it comes to managing those different chemicals after its service life, it's where it becomes challenging, and it becomes a headache for like a solid waste engineer like me working in this field. So we have to, in terms of trying to come up with remediation of that, come up with cleanup and all that. Of course, it does it does generate revenue. It just add to GDP. So those things are there, but even if you can come up with a better industry of not contaminating, that will be always better. So, so there is a hazard. We call it hazard identification. Which what is hazard? It could be premature death, disease, disability due to chemical exposure. So that's your hazard. Risk is what is actual risk and what is perceived risk. So we'll talk about that. What is the actual risk from there for certain things? So these are some chemicals which are very common in terms of their their toxicity. Nanoparticles is also added to that. These are some historical chemicals which people learn a lot. People do a lot of research on in terms of different, different like toxicity of these different contaminants. So toxicology is a study of how chemicals reduces an organism's ability to survive and reproduce. So you can have an adverse effect, and you can the poisons, the chemicals which can create adverse effect. So in terms of toxicology, there is something. These are some of the basic definition. Toxicant, a toxic substance that is man-made. Toxin, a toxic substance produced by living organisms. There could be acute or chronic. Acute means short, single exposure. Chronic means long exposure. Latency is the time between exposure and the response. So what is toxic? Everything is toxic to a certain extent. A famous quote is that all substances are poisons. There is none which is not a poison. The right dose differentiates a poisons from a remedy. So that's even water is poison. If you consume too much of water is a poison. Too much oxygen is a poison. That's why if you have too much of free radical, free oxygen, excuse me, free oxygen radical at in your system, that also creates your flesh. It starts getting oxidized. So that's also a problem. And of course, we have DDT, lead, and other things are problem too. So what is the toxicology that what is the toxicants? What are the more major things? What is the characteristics it should have? It must be present in the environment. It should be bioavailable, bioaccumulated. It should interact with it at a molecular site with the body where it is trying to have a negative impact. May cause metabolic dysfunction, must decrease the fitness. So these are some of the characteristics. So how we already kind of talked about the release, so we'll not get there. We also talked about environmental fate in terms of partition, transport, and transform. So these things does affect your exposure level. So here, if you look at an example, so you have different things happening. You have we have a industry which release certain chemicals into the atmosphere and into the water bodies. We have this like boats and other stuff. We have fisheries going on. So we add a lot of different things into the environment in terms of pollution. From the air pollution, there is a rainfall that also goes in there, and the smaller particles are there, which dissolved particles or particles in suspension. Many times they come together and form colloids, and then there is that's kind of its fate. It can be eaten up by the water of different water species present, or it can bioaccumulate within the water as water species, as we talked about methyl mercury in the fish. So there are different things that happens for any particular contaminant. So, and you can get exposed to different things like skin. You can go to respiratory exposure. You can get injection, accidental, intentional. Those things are also there. Food that is there. So characteristics is if something has large surface area and if it's highly vascular, it becomes it's actually it's a problematic stuff from a toxicology point of view, from its risk point of view. And nanoparticles kind of fits in the bill right there. It has large surface area It also there are nanoparticles which could be highly vascular too. So once you get exposed to it, your body starts working on it. The body tries to remove it out in terms of urine, in terms of exhaling, in terms of other eliminations. Even it could go through the fecal matter as well. So body tries to eliminate this contaminant as much as possible. But while it is going through the body, it does interface with normal receptors. So there's a neuroreceptors, endocrine disruptors are there, enzymes transport. It can interference with membrane function, interference with cellular energy function, binding to biomolecules. So these are some of the different things that it can do while these contaminants are passing through our system. If it's too much of if it's the impact is too high, it can even lead to death. You can even lose one organ or tissue damage. It can lead to different types of disease. Could be others response as well. So in general, when we go for like body keeps on repairing itself, so functional cell replacement is there. Fibrosis, scarring of the and connective tissues. So that's also does take place. So we talked about that one of the response could be death, irritation, allergic, carcinogen, tetragonic, reproductive impact, neurotoxic impact. Other organ systems could be impacted too. So what is risk assessment? So I kind of talked about that. Now we'll try to summarize it and then look at an example, look at the scenario of nanoparticle, a particular like how these all relates to nanoparticle. We'll try to go over that. So risk assessment is a process where site-specific information on chemical contamination and exposure are used to estimate the potential risk at a contaminated site, or so that you can manage that possibly manage that easily, or you can come up with a management system for it. So hazard is an unwanted adverse event. It could be chemical, it could be biological, it could be physical hazard as well. Risk is the likelihood of an unwanted occurrence and an uncertainty about when this event might occur. Safety is about minimizing risk and eliminating hazard. So that's what we are talking about. So risk assessment, as I said earlier, we have to look at, there are 4 steps. We kind of already covered hazard identification. We covered dose response evaluation as well. We have been discussing about exposure assessment. Now we'll talk more on risk characterization and risk management. So that's so some of the examples before in terms of these. This is one example of Pcbs, which is again, if you have this is the most widespread chemical contaminant known from the factories into the waterways and all that. It is threat to human health and the environment, can cause a skin disorder. It's an endocrine disruptor as well. So if you have to go for say if you have a water body contaminated with that, you have to again follow these 4 steps. As a hazard identification, we have identified Pcbs could be the problem. And then dose response evaluation. What is the concentration of Pcbs there? What is the fate of Pcbs in there? What are the reactions taking place there? So we have to take that and relate it to our requirement. And then based on those information, you take a decision in terms of what to go about, how to go about chemical remediation or biological remediation of that particular place. So it's a threat to health, as you can talk about. Then dioxins, another bigger one. So there are a lot of chemicals out there which I just wanted to give you some example. It was a contaminant byproduct in production of herbicides as Agent Orange, and it was used to clear jungle vegetation during Vietnam War. It can cause a skin disorder. It's a different types of toxicity, endocrine disruptor, suppression of immune system, and all those things are there. Presently, Ukraine is in news, isn't it? Because of the war that is going on between Ukraine and Russia. But this is not Ukraine and Russia. The rivalry is not new. It has been going on for quite some time. So as you can see over here, Viktor Yushchenko is his photo in March 2002 on the left-hand side, and the same gentleman is there on the right-hand side. The same gentleman which is on the left-hand side is also there in the right-hand side. And that's in the period of 2002 to December 2004. So we are looking at what, 12 plus 9, around 20, 21 months. In 20-21 months, you look that nice looking gentleman, such a young face, got converted to this face because of the dioxin poisoning. And it is said that he was scarred by deliberate dioxin poisoning during his 2004 presidential candidacy, and it was essentially done by Russians. So Russian agents got into his his own personal staff, and in terms of they started feeding him dioxins, and then the gentleman did not survive for long, and then and then he could not serve as a president as well. So because he was this Viktor Yushchenko was actually anti-Russia. So right, this is the present president of Ukraine is also like that. So that's why you are seeing that problem coming up there. Other common example which is used a lot, which is again, I put this example towards the end of this segment before we jump to nanoparticle, is because of many times when we relate nanoparticle toxicity with other toxicity, this example comes, asbestos. Example come that actually this carbon nanotube, it is showing similar toxicity tendency, similar risk tendency as asbestos. So asbestos people are using it for quite some time. 80% it's used for fireproofing and all that, but it does create, especially during the manufacturing of asbestos seeds, and as trying to get these asbestos fibers out from the mining activities and all that. So that's where it creates asbestosis, which is the scarring of lung tissue, and it can cause lung cancer. Exposure risk 7 times more and if somebody is smoking cigarette as well and gets exposed to this asbestos, then the chances are even 60 times higher. So it does create cancer. It's like a mesothelioma, cancer of lung or stomach lining. Asbestos is only known cause for mesothelioma, and then it can be fatal within 2 years of diagnosis. Lead is another one which is very common. Lead is also used in some nanoparticles too. It impairs brain function. It interferes with blood cell formation, kidney damage. It has been found that the number of lead in number of children over the years has gone down. We have seen that if somebody has exposure to higher amount of lead, that person becomes irritated very quickly. So his cognitive function starts getting compromised. So he can become he has to go see doctors on a regular basis. So this lead is creating a lot of issue. That's why has been creating a lot of issue. That's why we have been trying to phase out lead from different applications. When you go to a petrol pump, you see written there unleaded. Why it is written unleaded? Because there was lead in petrol or diesel at some point of time, but we have kind of removed that lead. And as the lead is removed from the system, we see less and less lead in the blood samples of children, as you can see in this particular graph, and less lead in the children's better response in the classroom. They behave better in the classroom. They concentrate in the classroom and all that, because lead impacts your brain function. Now, you saw all that, like you had a kind of discussion around risk assessment in general. Now, when we try to take this and try to use it from a nanomaterial point of view, what are the challenges? First of all, size. It's pretty small size, less than 100 nanometer. So first of all, defining nanomaterials. Structures, what kind of structure we are looking at, the property of the nanoparticle, whether we're talking about single particle, agglomerate particle, aggregate particle, whether it will transform, whether nano will get converted to ionic. So a lot of questions are there, and those kind of questions need to be answered when we look at these risk assessment. So you look at how do you measure exposure, in whether we are looking at mass or numbers, surface area, how you will distinguish between engineered materials from the background nanoparticle sizes, because they have been around for a while. lack of fate transport and uptake data. We talked about the solubility data, coating, surface charge, and bioavailability, translocation, toxic effects. We don't know much. Many of these things we are.
Sir,
Many.
you can mute them. Sir.
Yeah.
Mute the participants. Yeah.
Let me see. I may have to stop sharing.
Someone, yeah, no issues, sir. I think they left, it seems. Yeah.
Okay. Oops, I went to the wrong. Anyway, I'll go to let's put from current slide. Yeah, we went there. Okay. So, trying to understand the background of those nano-sized particle as well. We don't have much data in terms of the fate transport. So that's what a lot of research is going on, try to understand fate transport. So, and that's what you will hear from other in other units of this particular program about some of the research work that has been done in terms of fate transport of these nanoparticles. And nanoparticles are used quite a bit in remediation application too, especially nano iron. Nano iron is used extensively for removal for treating organic contaminants in subsurface. So understanding of fate and transport is not only from a toxicity point of view is important, it is also important when you try to design remediation system using nanoparticles. Because if you know what will happen to the nanoparticle, you can design your system better. And if you can know how it will transport, again, you can it will help you to design your system better. So in one of the PhD student working with me right now is actually focusing on this transport of nanoparticle, I say from a remediation application point of view. So maybe in a couple of by the end of this year, he should be able to finish, and then we'll be able to see some papers coming out from there too. So nanoparticles, the workers can get exposed during the handling of production. So the production of lab factory discharge leakage, worker can get exposed. Transport discharge leakage, again, workers, storage. Then we have the products. Then this is waste discharge leakage. So that can bring to the transport diffusion, all coming to the atmosphere. Then it in transformation degradation, it can go into the water bodies, it can come to the soil area as well. Then in the product, the consumer can get exposed during its product, the release of fixed nanoparticle in there. Then it can from consumer because of the things happening like fate and transport into the environment. Things can get into the air phase, water phase, into the diet, and from all these different phases, the consumer gets affected. Okay, let me. Sahani Reddy, if you can mute yourself.
Sir, on to the right, you can mute everyone. Sir. I think there is an option for you. In the bottom of the participants, you can mute everyone.
Yes, I have to unshare, isn't it? You have to stop share to do that.
Yes, sir. No, on to the, yeah. I think on the bottom.
Yeah, mute all.
Yeah.
And then I think I have to unmute myself. No, I'm already unmuted. Okay. So I'll go back to my share screen. So these are the different exposure that we are looking at. But to find out, again, when they are in the air, in the water, in the diet, whether it's in the nano form, whether it's in the ionic form, whether it's in the colloidal form, we don't know. So those are things which we need to kind of understand in terms of the nanoparticle. So those things we look at. And this in different in this engineered nanoparticle in different environmental biological matrices, from inhalation, ingestion, dermal, they can get into the human body and then can have can interact with several of our human body systems, and then have variety of health impacts which people have based on. These are all based on the lab-based studies on different species which has been already been done. So it's toxicity of a nanoparticle also depends on the size of nanoparticle. In fact, that was, I'm pretty sure Dr. Pokharel will definitely talk about that, because that was again part of his thesis, where we looked at the different sizes of nanoparticle. Lower the size, we found more the toxicity. And then also the stability of nanoparticle, like what kind of coating it had, the coating material. Whether, for example, nano silver, you can have for the nano silver, you can have citrate coated, you can have PVP coated. So based on the different coating material, the toxicity was also different. So toxic interaction was different. So when we did some of the toxicity test in the lab. So that's so chemical composition and crystalline structure, surface coating may change the physicochemical properties, affecting their toxicity. SAPE, toxic interaction with cell can be enhanced due to the SAPE. Aspect ratio, size, we talked about that. Surface area, reactivity of nanoparticle grows with increasing surface area. So that's again toxicity of the material goes there. Then just a second. Sorry for that. I don't know why she is unmuting her all the time. So in terms of properties, as we were looking at for the ionic as well, same thing goes for nanoparticle, like solubility.
Sir, you can remove her. You can remove her, I think.
Okay, how to, just a minute.
So there would be a more option, and then if you click that, then there would be.
Yeah, I think even I can just go to her Sahani Reddy, yeah. And you can just remove.
Yeah, perfect.
Okay. Now I go back to my share screen. Okay. So so in terms of your nanomaterial properties and toxicity, solubility, it can increase or decrease toxicity depending on the mode of action. Like if it gets solubilized in, if it can get into our bloodstream and all that, and it goes into our different cells, or if it becomes part of our excreta system, like excretion system, then it basically will go out of the system. Surface area associated with lung inflammation, we have found in rats and mice, cancer in rats. Surface reactivity, size, usually lower the size, more the toxicity. Shape, that also can influence deposition. Volume, that again, it has been found in rats that it does affect. Mass, how much mass is present, those metric of use in toxicological studies. The number as well, like those number of particles present, or number of the mass present. So those are the different terminology we kind of look at. So whenever we try to go for these nanoparticle toxicity, first of all, we had looking at exposure, fate kinetics, the hazard. So you look at the data evaluation, you evaluate the data, you generate a lot of data in terms of lab-based studies. And taking that lab-based studies, you try to come up with like what kind of, it's kind of interchangeable, the phase 1 and phase 2, where you collect all these data and then you try to come up with risk characterization based on the lab-based data. Then you try to extrapolate the data to human level and try to do the risk characterization and come up with what will be safe level and all that. So this is kind of big, this is how any risk assessment protocol is done. So again, I think this is potentially the last slide. So in terms of, again, I will just try to summarize. When you go for risk analysis or risk correct management, one thing is that you have to, first of all, you need to find out what is the hazard. What are the chemicals present? What are the chemicals present, and in what concentration it is present? So hazard identification. And for the hazard identification, you have to do proper sampling to get that hazard identification. Then you go for dose rest, like a exposure, so concentration level. You can get the concentration level, you get the exposure duration, what setting it is, and then you based on the potency of that, we calculate the toxic potential toxic impacts. Then we can, based on the exposure concentration which is available to us with the data collected, we can compare it with the risk-based standard. Risk-based standard developed using mostly using the lab-based study with Lowell that you saw the dose response curve. And if it's below that, the risk is not there. If it's above that, then risk is there. Then we start managing the risk in terms of reducing the frequency of exposure, or try to do the remediation system of trying to clean it up. So that's how the whole thing works. So fate, transport, exposure, and all these things are important when you go for any of these risk analysis or risk management. So thank you. I actually, yeah, so we have around 15, 20 minutes of Q&A. I try to keep it that way so that on purpose, I wanted to have some time for question and answer, because otherwise it becomes a one-way traffic. So I hope you will have some questions so with that we can discuss. And any question you can, I say in my class that no question is a wrong question, and no answer is a wrong answer in class discussion. When you take the exam, of course, there is a right answer and a wrong answer. But in the class discussion, no answer is a wrong answer, because we should look at the thought process behind that answer. So like how the person is answering that particular question. So again, you will see me tomorrow on where I will be giving you a kind of overview of what is a life cycle assessment, how the life cycle assessment is done. But for now, I would be I would be happy to take some questions or some comments. Was it useful? Was it not useful? Anything you want to say?
Yeah. Sir, what would be the standard book for risk assessment?
So a standard book for risk assessment, there is there are like if you just Google, there are actually a lot of books are out there. But any environmental like even if you want to start with the basic of even if you take a basic environmental engineering book, where they will talk about risk assessment as part of the water quality, air quality, and all that. But there are specific books out there. If you want a name, I can like I can provide you the name, and we can kind of let me see. There are I'm not remembering the name of the author right now, but there are several books out there. If you can put uh, even there are Indian authors, there are foreign authors. So if you look at in terms of environmental risk assessment, and then when you go for risk assessment, there are different types of risk as well. See, there is one risk. What we are talking about is environmental risk assessment. There are risks even from your risk from in financial risk. Financial risk is also there, isn't it? There is a financial risk which people talk about in there too. So if you look at one particular book, which is from a it's environmental or ecological risk assessment, there is one Gallen W. Shooter, SUTER. His book is one of the older book on environmental risk assessment. Then there is a book called by Ted Simon as well, which is again on environmental risk assessment. So if you go to any library, you will find books on environmental risk. And there are a lot of information available on the internet as well. Like if you, but internet, you have to be careful where you get the information. US EPA has a nice guideline. US EPA has a nice guideline document on environmental risk assessment too. So you can use, and European Union also has a nice guideline on environmental risk assessment. So you can download those reports and use that. So that's those things are available. And as as you saw in my contact is there in my last slide, and you will. Again tomorrow it will there, so you can always you can find me if you are doing any risk assessment work and you need any help at any time, you in terms of any guideline or guidance, you can always get in touch. We'll be more than happy to help you on that.
Okay, sir. Okay. Yeah, participants.
I think
you can
Jagdish,
drop your question in the chat box as well. Yeah.
Hello,
Jagdish, yeah, he had unmuted himself. Yeah, Jagdish.
Good evening, sir. Sir, I would like to ask a question regarding risk assessment. Sir, how to carry out the risk assessment for a new pollutant, like for example, nanoparticles?
Yeah, so that's again, as I was trying to explain, that you need to get all those data, isn't it? So you need to find out, you need to do a lot of, for any pollutant is a new pollutant at the first time. Even when first time arsenic was, people were studying arsenic, it was a new pollutant. First time people were studying lead, it was a new pollutant, isn't it? So there is a basic steps. The first step is you have to find out, okay, what is the level of exposure which is out there in the environment? What could be the potential level of concentration? So when this new contaminant comes into the environment, the first thing is to develop the analytical capability. Analyticals, whether we will be able to measure it. And with the nanoparticles, the problem is also that whether you're measuring it as a nanoparticle or a ionic particle, because most of this nanoparticle is derived from ionic form. So you have to find out that too. So analytical part, come up with the analytical technique to analyze for these nanoparticle. That's the number one. And find out what is its concentration. Now, once we have some idea of what is the typical concentration available in the environmental system, we go back to the lab and we use this rats, mice, guinea pigs, and all those different species, like we have used it for arsenic and other things too, and we expose them with these nanoparticles. And this work has been going on for last almost 20 years now. You will find a lot of literature, a lot of papers you will find on environmental toxicity and all that, and so of nanoparticles. So you get lab-based data in terms of at what level it is showing negative impact on these species. Then there is a statistical method of taking that concentration level and extrapolate it to the human level. We talked about all the uncertainty factors. So you apply all those uncertainty factors, you come up with what is the human level like a risk in terms of concern. What will be the safe level for humans? And then we go for what is the safe level, how it compares with what is the concentration is there in the environment. If the concentration in the environment is less than the safe level, we are okay. If it is more than the safe level, then we have to come up with a remediation system. So that's the whole risk assessment, risk characterization or risk management, you can say, for any contaminant, because any contaminant is a new contaminant at the first time. So I hope.
So similarly for nanoplastics also, can we do like
yes,
the risk
we can
assessment?
do that. We can do nanoplastic risk assessment too. Nanoplastic, microplastics, that is also there. Even Dr. Barney is doing some work in that area. One of my student, Varaprasad, is also trying to do some work. Where we have one student from Professor Sudha Goyal in our department in civil engineering. He was looking at some of this work too. So yeah, there are, and then you will find a lot of papers, a lot of people working on this, because plastics, microplastics, it's a hot topic right now. And we don't know much about this right now. So we try to understand with, again, similar approach, but with microplastics, with nanoplastics. And for plastics, I don't know whether you have seen, we have a NPTEL course. I assume that you're familiar with NPTEL SWAYAM platform. We have
Yes,
an
sir. Yes, sir.
yeah, we have
I
an
have taken
NPTEL.
your courses, sir.
Oh, okay, good. So I'm sorry. So maybe the first part of the lecture you have already seen that.
Yes, sir.
So so it was a revision. It was a revision for you.
Yes, sir.
So yeah. Okay.
Thank you, sir.
Okay. Yeah, and I think there was some other person who had. I think it was Srinivashan who had it muted.
Yes, sir. Nice to meet you, sir, after a long time. So I'm here in the Department of Biotechnology, sir.
Okay. Okay.
So I was interested in this nanotoxicology field. I have written, I have spent some, almost some 6 months there, sir, for writing one article. So there I could see the gold nanoparticle of sizes of very close in range, sir. Let's say 6, 10, and 14 or something like that. And among them itself, one size is very peculiar. It can able to get into the cell system very easily, but the smaller one and the bigger one and does not show that kind of efficiency. And if we see other papers, done by another people, they have set up this data. So there itself, there is a clumsiness in the data set. So, we cannot able to do the studies on all the nanoparticle or the different sizes, what we can do, because the size control is itself, it's a difficult task in that synthesis.
Yeah.
And one more thing, like the particle, as it become very smaller and smaller, the reactive nature of the particle is also going to be exposed. So any secondary pollutants which is lying over that surfaces reduced in the reactive form, or that also causes other type of inflammation in the cells, like that I read, sir. So these discrepancies, the clumsiness in the data, like how we are going to have like you have explained the framework in terms of environment, but in the cell study itself, this much clumsiness existing. So how do you see, sir, this one? And then, how do you go about this one? That is what I would like to know, sir.
Yeah, so it's a this again can lead to lot many PhDs in coming future, because that's what it is, isn't it? So it is there. It is definitely there. So when you talk about the different sizes, different papers showing different results, again we have to be very carefully look at how it was done. When one of the initial thing that we saw when I started working on nanoparticle in I would say in 2006-7, when I first started, I was asked to, actually there was one conference happening, and they wanted somebody to just do a quick review and presentation on nano waste. My area is my area is essentially waste management, which you may have, if you know me, I'm essentially a waste management guy. I call myself a garbologist, working with different garbage. so when I was working with the garbage, then this nanoparticle containing waste started coming in. People were worried about what will happen with this nano waste in the landfill. So that's how I got into this nano business. And then when I started looking at, I found that not clarity. Now, today we have slightly better clarity. 10-15 years is too less of a time for a research and development time frame, isn't it? It takes a lot of time to really understand things. But there we found that many papers were reporting this nanotoxicity value, but that stability part was not there. There was no zeta potential. The size was also not there. So it was becoming difficult to really and to trust those data, because although they were the first papers of nanoparticle toxicity, so they did get published in very good journals, but because they were the first ones. But still, if you look at today, probably the same journals will not publish them. If the same work is done today by somebody, will not publish them, because it has a lot of, as you rightly mentioned, it has a lot of holes in that. Things are not very clear. But gradually people started looking at how to look at purity of nanoparticle, how to look at the long-term stability, do the DLS data and your data potential. You make nanoparticles today, but you are doing your toxicity test, say 1 week from now, 2 weeks from now. So you have to monitor whether the nanoparticle is still stable. So those things started coming up. So you start in some of the newer work, you do see that things are becoming better. Things are more and more clarity is coming. So again, it's a work in progress. Some of the biological stuff in terms of the interaction with cell and all that, I am not a biologist, so I'm a little bit not that much sure about that. But but I have seen those. What you're suggesting, I have seen that too. Like usually, if we say that lower the size, higher the toxicity, that is also not true all the time. Because how it interacts, what kind of mechanism is happening, what kind of things. Maybe when it's too small, it just passes through the system. It does not interact. It just gets through the system. So since it does not interact, there is no toxicity. So those things are there. Again, we have to learn based on different experiments. We have to design, set up some experiments and do those kind of stuff and learn some more. Hopefully some students, if they are in the audience, if they get excited about it, they can come forward and do some PhD in this area. In India, still this area is relatively, I would say, new. Some people are there who are working in this area, but not many people are doing, especially from the toxicity and all that, nanotoxicity, all we don't. So there is a lot of scope of work in this particular area right now.
Okay. Thank you, sir.
Yeah. Any other question?
I think no, sir. So I think I can ask the participants if you have any questions, kindly note it down, then so that before tomorrow's session you can just be prepared, or otherwise once after the tomorrow session you can drop him a message, and then so that it can get clarified. So I think I take this opportunity to thank Professor Dubey to set in early hours and then to convey the lecture. Thank you, sir. Thanks a lot. And we can wind up the session, and then tomorrow we can start with the fourth, that is, yeah, the fourth lecture of this series.
Okay.
Okay, sir. So thank you, sir.
Thank you.
And then have a nice day, sir. Yeah. Have a quick sleep and then have a nice day. Yeah.
Yeah.
Okay, sir.
Okay. Thank
Okay,
you.
sir.
Okay. Bye.